The 12th of August, 1943. Somewhere over the North Sea, at an altitude of 14,000 feet and a temperature of -22 degrees Celsius, a de Havilland mosquito cuts through the pre-dawn darkness at nearly 400 miles per hour. Its two Rolls-Royce Merlin engines are running at near maximum power, their exhaust stacks glowing faint amber against the black sky. The aircraft carries no bombs. It carries no guns of consequence. Its bomb bay has been modified to accommodate additional fuel tanks, extending its range to an almost improbable 1,500 miles. What it does carry, what its sole purpose for being in that frozen, hostile sky amounts to, is a set of instruments and a very particular pilot. Flight Lieutenant Douglas Gilchrist checks his altimeter, adjusts his oxygen mask, and peers through the Perspex windscreen at a sky that most men would have found utterly featureless and indifferent. But Gilchrist sees something else entirely. He sees data. He sees pressure gradients and humidity readings and the particular character of the cloud formations building 40 miles to the northeast. He reaches for the wireless key and begins to transmit, in cipher, a sequence of readings that will travel back to England within minutes. Nobody on the German radar stations below can quite make sense of this lone aircraft's behavior. It makes no bombing run. It drops no mines. It photographs nothing that they can detect. It simply turns and goes home. They file it as an anomaly and move on to other concerns. They have made, in this moment, one of the most consequential misjudgments of the entire war. The information that Gilchrist has just transmitted is destined for a building in Dunstable, Bedfordshire, where a group of men and women who would scarcely have been described as warriors by any conventional measure are doing something that their enemies have not yet fully appreciated. They are turning the weather into a weapon. To understand why this matters, why a set of barometric pressure readings and cloud-based estimates could be worth the life of a highly trained pilot and one of Britain's most capable aircraft, one must first understand the extraordinary degree to which the Second World War was fought in, by, and against the atmosphere. Every bomber raid depended on weather. Every naval engagement was shaped by it. Paratroop operations, amphibious landings, submarine patrols, and fighter sweeps all lived or died by conditions that no amount of courage or engineering could override. A bombing force dispatched into an unexpected storm front might lose half its aircraft to icing alone before a single German gun had fired. A fleet that found itself in unexpectedly rough seas at a critical moment could be rendered impotent regardless of its firepower. The weather was, in the most literal sense, a force multiplier, or, if misread, a force destroyer. What Britain came to understand, with a sophistication that outpaced almost every other nation in the conflict, was that the weather itself could be weaponized. Not in some fantastical science fiction sense of controlling or manufacturing meteorological conditions, though some German scientists were indeed pursuing ideas of that kind, but in the far more practical and immediately devastating sense of knowing what the weather was going to do and ensuring that your enemy did not. The unit at the center of this effort was the Meteorological Office's Central Forecasting Office, working in close concert with the newly established Special Meteorological Sections embedded within RAF Bomber Command, Coastal Command, and ultimately with the Supreme Headquarters Allied Expeditionary Force itself. It was an organization born of necessity, built on expertise that predated the war by decades, and weaponized with a deliberateness that only became fully apparent after the conflict had ended. The British Meteorological Office had been a going concern since 1854, when Vice Admiral Robert Fitzroy, the same Fitzroy who had commanded HMS Beagle during Charles Darwin's famous voyage, established the first systematic program of weather observation in Britain. By the outbreak of the First World War, the office had developed a network of surface observation stations and a primitive but functional telegraphic reporting system that allowed forecasters in London to build synoptic charts, maps showing the state of the atmosphere across a broad area at a given moment. The science was imprecise by later standards, but the fundamental methodology was sound. You needed data from many points across a wide area, gathered simultaneously and reported rapidly, in order to understand what the atmosphere was doing and predict where it was going. The problem, as it had always been, was that the crucial data came from out over the ocean, where no observation stations existed and where the weather systems that would ultimately batter the British Isles were still forming, still organizing themselves into the depressions and fronts that would determine what happened on land. By 1939, this fundamental problem had not been solved so much as worked around, partially and imperfectly, by a series of arrangements with other nations and by the use of weather ships, vessels specifically tasked with sitting in the North Atlantic and transmitting meteorological observations. The Scandinavian nations, particularly Norway, maintained extensive networks of observation stations that provided invaluable upstream data on systems approaching from the west and northwest. Iceland and the Faroe Islands offered similar coverage of the high-latitude regions where some of the most violent and operationally significant weather originated. When Germany invaded Norway in April 1940 and subsequently occupied it, the implications for British meteorology were severe and immediate. Overnight, a substantial portion of the most valuable observational network in Europe was either silenced or worse, captured intact and turned to German use. The mathematics of this loss were brutal. A modern synoptic weather chart is only as good as the observations that underpin it, and an observation is only useful if it arrives in time to be incorporated into a forecast that can still influence decisions. In the pre-computer age, a forecaster working with observations from a 6-hour-old surface chart was already operating at a significant disadvantage. With the loss of the Norwegian network, the effective radius of reliable British meteorological knowledge contracted sharply eastward. Forecasters at Dunstable found themselves working with charts that had alarming blank spaces precisely where the critical Atlantic weather systems were developing. The Germans, conversely, now had access to Norwegian stations and to their own extensive network of Atlantic weather ships, vessels whose activities were, in the early part of the war, largely unknown to British intelligence. This asymmetry had consequences that were felt almost immediately in operational terms. The winter of 1940 to 1941 saw Bomber Command lose a disproportionate number of aircraft to weather-related causes, including icing, structural failure in turbulence, and navigational errors compounded by unexpected wind shifts. Precise figures for weather-related losses as a category distinct from enemy action are difficult to establish with certainty. The wartime records were not always scrupulous in distinguishing between the two, and a bomber that disappeared over Germany might have been shot down, have suffered an engine failure, or have simply lost its way in a storm and run out of fuel over the North Sea. What is clear is that operations planners at Bomber Command were receiving an uncomfortably high proportion of weather forecasts that proved, in practice, to be seriously inaccurate. The response to this problem, when it came, was characteristically British in its blend of improvisation, expertise, and what might politely be called controlled audacity. The decision was taken, at a level that required Air Ministry approval, to begin mounting dedicated meteorological reconnaissance flights, sorties whose sole purpose was to gather atmospheric data from regions where surface observations were unavailable. The aircraft selected for this role was the Bristol Blenheim initially, later superseded by the Supermarine Spitfire and ultimately the de Havilland Mosquito, each transition reflecting both the improving performance requirements for penetrating defended airspace and the refinement of understanding about what kinds of data were most valuable and where they needed to be gathered. The unit that emerged from this requirement was 1401 Flight, subsequently expanded and reorganized as 518 Squadron and its sister units, operating under the umbrella designation of the Meteorological Reconnaissance Flights. The men who flew these sorties occupied an unusual position within the RAF's hierarchy of glamour. They were not fighter aces, though many of them had flown fighters. They were not bomber crews, accumulating the grim arithmetic of operations towards their 30-mission tour. They flew alone, or in pairs, often without fighter escort, into some of the most hostile weather in the Northern Hemisphere, because the whole point was to fly into the weather, to measure it, to report it. A sortie that returned because the weather was too severe had failed in its fundamental purpose. The mathematics were pitiless in their logic. The flights themselves were given operational code names that reflected their geographic orientation. Pampa sorties covered the Atlantic approaches to the north and west of Britain. Epicure sorties penetrated into the Bay of Biscay. Mercer sorties surveyed the approaches from Iceland and Greenland. Each followed a prescribed pattern of altitudes and waypoints, with the pilot conducting systematic observations at each stage: barometric pressure, temperature, dew point, cloud types and their base heights, visibility, precipitation, wind speed and direction estimated from sea state. These observations were transmitted in cipher and received at Dunstable within minutes of being taken, where they were incorporated into the synoptic charts that formed the basis of operational forecasts. The value of this data was almost incalculable in operational terms, though the specific numbers are instructive. By 1942, Bomber Command was mounting operations on an average of 12 to 15 nights per month, with each operation involving between 100 and 400 aircraft. A forecast that was wrong by even 50 miles in placing a weather front, or wrong by 6 hours in timing its passage, could mean the difference between a successful attack and a catastrophic loss rate. The Augsburg raid of April 1942, in which 12 Lancaster bombers flew at low level in daylight, and 7 were shot down, has been attributed primarily to German fighter interception, which is true. But the weather conditions that forced the aircraft to fly at altitudes where they were visible and vulnerable were themselves a factor in the decision-making that led to those losses. Better meteorological intelligence did not guarantee better outcomes, but it substantially improved the odds. The German appreciation of what the British were doing was slower to develop than might have been expected of so scientifically sophisticated an adversary. The Luftwaffe maintained its own meteorological services, which were extensive and professionally competent. The Wehrmacht's meteorological organization, the Wetterdienst, had been planning for the operational requirements of a European war since the mid-1930s and had accumulated considerable expertise in short-range tactical forecasting. What the Germans were slower to appreciate was the degree to which the British were using their meteorological reconnaissance capability not merely to improve their own forecasts, but as a component of a broader intelligence operation that included the systematic denial of equivalent data to the enemy. This is where the story takes a turn that most histories of Second World War meteorology gloss over, because it is considerably stranger than the already remarkable tale of pilots flying into Atlantic storms to read thermometers. The British were not merely gathering weather data for their own use. They were, with increasing deliberateness, gathering it in ways designed to ensure that the Germans could not gather comparable data themselves. The campaign against German weather ships was a case in point. Between 1940 and 1944, the Royal Navy and Coastal Command conducted a series of operations specifically targeting the network of German meteorological vessels in the North Atlantic. Not because these ships were a direct military threat, for they were typically lightly armed auxiliary vessels, but because they were the primary means by which the German meteorological services maintained their observational coverage of the critical Atlantic source regions. The capture of the German weather ship München in May 1941 is well known to students of the intelligence war because it yielded enigma material of considerable value. Less celebrated but equally significant in meteorological terms was the capture of the weather ship Lauenburg in June of the same year, and the subsequent sinking or capture of a series of similar vessels over the following years. Each loss degraded the quality of German Atlantic observations. Each degradation made German operational forecasts marginally but cumulatively less reliable. The British, possessing both their own reconnaissance flights and the residual Allied surface observation network, which now included American stations as the United States entered the conflict, were progressively widening an information gap that the Germans could not easily close. The German response, when it came, was technically ingenious if operationally inadequate. The Wetterdienst began deploying automated weather stations, compact, buoy-like devices that could be landed from submarines on remote coastlines and would transmit meteorological data by radio for months without human intervention. These Wetterkurier and Kroter stations, as they were designated, were placed on the coasts of Greenland, Labrador, and Spitsbergen, in locations so remote that the Germans calculated their detection and destruction would be unlikely. One such station, WFL-26, was installed on the northern tip of Labrador in October 1943 and transmitted for several months before its batteries finally failed. It was not discovered until 1977, when a Canadian government survey team stumbled across it by chance. By then, of course, the war it had been built to serve had been over for 32 years. These automated stations were clever, but they could not replicate the quality of data obtained by a trained meteorological observer making systematic measurements across a series of altitudes and reporting in real time. They measured surface conditions only, could not describe the vertical structure of the atmosphere, and their data arrived with a time lag that reduced its value for short-range tactical forecasting. The British reconnaissance flights, by contrast, produced atmospheric profiles of considerable sophistication, including upper-air data that was essential for understanding the behavior of the jet stream, a feature of the upper troposphere whose influence on weather systems at lower altitudes was, by the early 1940s, beginning to be appreciated by the more forward-thinking meteorologists on both sides. The understanding of the jet stream's operational significance was, in fact, one of the quiet revolutions of wartime meteorology, and the British were at its forefront. The phenomenon itself, a narrow corridor of extremely fast-moving air at altitudes between 25,000 and 35,000 feet, had been noted by high-altitude balloon ascents in the late 19th century, and its existence was theoretically predicted by Norwegian meteorologist Wilhelm Bjerknes's polar front theory, which had been the foundation of modern synoptic meteorology since the First World War. But its practical implications for aircraft operations had not been systematically explored until wartime necessity forced the issue. A bomber flying at 20,000 feet could encounter tailwinds or headwinds of 100 miles per hour or more from jet stream influence, radically altering its ground speed, fuel consumption, and the accuracy of its navigation. The difference between a 100-mile-per-hour tailwind and a 100-mile-per-hour headwind amounted to a ground speed variation of 200 miles per hour on an aircraft whose airspeed might be 200 miles per hour itself. The navigational implications were profound. A dead-reckoning navigator calculating his position on the basis of an assumed wind speed that was wrong by 100 miles per hour would accumulate a positional error of 100 miles for every hour of flight. Over a round trip from England to the Ruhr, perhaps 4 hours each way, the cumulative error could be catastrophic. The British meteorological forecasting teams, working with data from the reconnaissance flights that now included systematic upper-air measurements, began building jet stream prediction into their operational forecasts. This capability, modest-sounding in description, enormously consequential in practice, was one of the factors that enabled the progressive improvement in Bomber Command's accuracy over Germany through 1942 and 1943. It was not the G navigation system alone, nor H-2S radar alone, nor the Pathfinder Force alone, that drove this improvement. It was the combination of all these technical advances with better meteorological intelligence that allowed each of them to function closer to its theoretical potential. The most dramatic illustration of the weapon that weather intelligence had become came not over Germany, but over France, on the night of the 5th and 6th of June, 1944. The decision to launch Operation Overlord, the Allied invasion of Normandy, on the date that it was ultimately launched, after a 24-hour postponement from the original date of the 5th of June, was one of the most consequential meteorological decisions in the history of warfare. General Eisenhower's chief meteorologist, Group Captain James Stagg, who led a team drawn from the British Meteorological Office, the U.S. Army Air Force's Weather Service, and the U.S. Navy Aerological Service, identified a narrow window of marginally acceptable weather that would open briefly in the otherwise stormy conditions prevailing over the English Channel. The original 5th of June date had to be abandoned because conditions were wholly unsuitable. The same storm that was prompting Eisenhower's agonized deliberations was simultaneously persuading the German commander in Normandy, Erwin Rommel, to travel to Germany on leave, confident that no invasion was possible in such weather. It is worth dwelling on this for a moment, because the asymmetry in meteorological intelligence is nowhere more starkly illustrated. Stagg's team, working with Atlantic reconnaissance data and a surface observation network that spanned 2 continents, could see the brief clearing approaching behind the storm system. The German meteorological services, operating without adequate Atlantic coverage and without the reconnaissance data that the British had been systematically accumulating, could not. They saw only the storm currently battering the Channel and projected its continuation. Rommel departed for Germany. The paratroopers boarded their aircraft. The fleet put to sea. The window, brief and marginal and barely adequate, waves still running at 3 to 4 feet, winds still gusting to force 4, opened just enough. The rest is history, though the meteorological intelligence that made it possible is rarely accorded its proper place in the telling. The human dimension of this achievement is worth examining in some detail, because it was the product not of a single genius or a single inspired moment, but of years of institutional development and the cultivation of a particular kind of expertise. James Stagg himself was a career meteorologist who had spent the interwar years with the Meteorological Office and had served in the Arctic in connection with scientific expeditions before the war. His authority, and the confidence that Eisenhower placed in his judgments, rested not merely on his technical competence, but on the credibility that the entire British meteorological system had accumulated through its wartime performance. When Stagg told Eisenhower that there would be a window, Eisenhower believed him, not on faith, but on the basis of a track record that included years of operational forecasting in direct support of some of the most demanding operations the war had produced. The cost of building this capability had been considerable. The meteorological reconnaissance flights had lost pilots and aircraft at a rate that, while lower in absolute terms than that of frontline bomber or fighter units, was nonetheless significant and sustained. 518 Squadron alone lost numerous aircraft during its operations, and the individual stories of these losses are often harrowing in their particularity. A pilot who had flown 37 successful Atlantic reconnaissance sorties might be lost on the 38th, not to enemy action, but to the weather itself, the very subject of his expertise. Icing at altitude could bring down a mosquito with the same terminal efficiency as a burst of cannon fire. Sudden deterioration in visibility could destroy a pilot's spatial orientation and send him spiraling into the sea before he had time to recognize what was happening. These men died in 1s and 2s without the recognition accorded to bomber crews or fighter pilots, their contributions largely invisible to the public and to history. The German program of strategic meteorological denial, which is how the British internally characterized their campaign against German observational capabilities, extended beyond the North Atlantic to encompass the Arctic. The Greenland ice cap and the Norwegian archipelago of Svalbard, known to the British as Spitsbergen, were the subject of a remarkable series of covert operations by both sides, each attempting to establish or maintain meteorological observation stations in these remote and inhospitable regions, while simultaneously disrupting or destroying the opponent's equivalents. The British established a series of covert Norwegian weather stations, staffed by Norwegian volunteers working under British direction in isolated fjords along the Greenland coast and in northern Norway itself. These stations, supplied by submarine or by small boats operating under cover of Arctic darkness, transmitted observations that were of direct value to Allied forecasters, while denying the Germans the meteorological understanding they needed to support their own operations in northern waters. The German counter-effort was persistent, if ultimately unsuccessful. A series of submarine-landed expeditions attempted to establish automated and sometimes manned stations across the Arctic, and several succeeded for periods of weeks or months before being detected and destroyed, or simply succumbing to the brutal physical conditions. Operation Bassgeiger, in the autumn of 1943, succeeded in establishing a manned German station on the northeast coast of Greenland, where a party of 10 men spent months transmitting weather data before Allied forces located and forced their evacuation. The story of these Arctic operations, played out in conditions of extreme cold, total darkness for months at a time, and complete isolation, has the quality of a particularly bleak adventure narrative, but its operational significance was real. Every week that a German station transmitted was a week in which German forecasters had marginally better data. Every week that it was silent was a week in which that advantage was denied. By the final year of the war, the British meteorological intelligence apparatus had evolved into something that bore very little resemblance to what it had been in 1939. The Dunstable Centre was receiving and processing thousands of observations per day from a network that now spanned the entire Atlantic, incorporated American stations from Newfoundland to Bermuda to the Azores, and drew on upper-air data from radiosonde balloon ascents as well as aircraft reconnaissance. The forecasting methods themselves had advanced substantially, informed by wartime research into the dynamics of frontal systems, the behavior of the jet stream, and the relationship between large-scale atmospheric circulation patterns and surface weather conditions. Forecasters who had begun the war working from rules of thumb accumulated over decades of practical experience were now working with theoretical frameworks that would not have been recognized by their pre-war selves. The legacy of this wartime development was substantial and lasting. The meteorological reconnaissance flight program did not end with the cessation of hostilities. It evolved instead into the peacetime network of weather reconnaissance operations that continue to the present day, now conducted primarily by remotely sensed satellite data and automated ocean buoys, but retaining in their conceptual architecture the fundamental insight that drove the wartime program, namely, that accurate weather prediction is impossible without comprehensive observational coverage of the regions where weather systems originate, and that such coverage must be obtained by whatever means are available at whatever cost is necessary. The RAF's meteorological flight program formally ended in the early 1960s, when satellite meteorology had advanced to the point where continuous atmospheric observation from orbit made piloted reconnaissance flights redundant for most purposes. The last operational meteorological reconnaissance flight sorties were conducted by Avro Shackletons operating from St. Evil in Cornwall, the same general operating area from which their wartime predecessors had departed on their Pampa and Epicure sorties 2 decades earlier. A handful of the Mosquitoes that had flown the wartime Atlantic sorties survive in museum collections, though none of the specific aircraft that flew the critical D-Day approach meteorological reconnaissance have been definitively identified among the survivors. The records of individual sortie aircraft are, in many cases, incomplete, a characteristic archival consequence of wartime operations conducted at the margins of the possible. The scientific legacy is considerably easier to trace. The wartime expansion of upper-air observation, driven directly by the operational requirements of the meteorological reconnaissance program and the practical need to understand jet stream behavior for navigation purposes, provided the empirical foundation for the post-war development of numerical weather prediction. The theoretical framework for solving the equations of atmospheric motion by numerical computation had been proposed by Lewis Fry Richardson as early as 1922, but the lack of sufficient observational data and the absence of computational power adequate to the task had rendered it impractical. The wartime accumulation of upper-air data, combined with the post-war development of electronic computers, made Richardson's vision achievable. The first successful numerical weather forecast was completed by a team led by Jule Charney at Princeton in 1950, using data of a type and density that would not have been available without the wartime observational program. The meteorological infrastructure built under operational necessity became the scientific infrastructure of the modern age. What remains, beyond the statistics and the operational history and the scientific legacy, is a question about the nature of intelligence and the many forms that weaponization can take. The conventional history of wartime intelligence focuses, understandably, on the spectacular, on Ultra and Bletchley Park, on double agents and deception operations, on the elaborate apparatus of espionage and counter-espionage that stretched across occupied Europe. These things were real and consequential, but running alongside them, quieter and less glamorous, and in some ways more fundamental, was the intelligence of the atmosphere itself, the patient accumulation and exploitation of knowledge about what the sky was going to do, and the denial of that knowledge to an enemy who did not fully appreciate, until too late, how completely he had been outmaneuvered in the most ancient of all the dimensions of war. The weather, in the end, does not recognize nationality. It does not take sides. A depression forming in the central Atlantic will produce the same gales and the same cloud whether a British or a German fleet lies in its path. The difference that won campaigns and, arguably, the war itself, lay in who understood that depression first, who had the data to see it coming, who had built the systems and trained the people, and accepted the cost necessary to translate the language of the atmosphere into the language of operational advantage. James Stagg, reading his charts in the early hours of the 5th of June, did not command any aircraft or any ship. He commanded only knowledge. It proved in the event to be enough. The lone mosquito that Gilchrist flew back to England in the summer of 1943 left no visible trace on the sky it had crossed. The readings he transmitted were incorporated into a synoptic chart, helped to shape a forecast, influenced an operation whose details will never now be known. This is how the weapon worked, invisibly, incrementally, through the accumulation of data so routine in its collection and so vital in its application that it became, for those who understood it, as decisive as any bomb ever dropped or any shell ever fired. The sky itself, that indifferent and omnipresent adversary, had been turned at last into an ally. Share.